Fine. So let's see how to do those kinds of Okay. One type of limit that we haven't covered. Remember, this is still part of 2.3. It's still part of it, continued. Something called squeeze theorem. Squeeze theorem. Sometimes it's called the sandwich theorem. See, both are good names. Both are good names for it. Okay. Well, let's start really with an example. Let's get the screen going. Okay. So let's start with really an example. Limit as x goes to 0 from the right. X cubed cosine of 2 over x. Okay. It's a good idea to just plug in 0. Let's, just to see where we're at. Maybe we're lucky, but if we just plug in 0 cubed cosine of 2 over 0. Okay, well, 2 over 0 is like c over 0. We do know how to deal with that. So those are like infinity minus infinity kind of things. Those types of limits. But then the answer is not necessarily plus or minus infinity because we're taking the cosine of it. So we're taking the cosine, let's say, of really big numbers. Yeah. Safel, you had a question or an answer?
Can you just make a sine over x over 2? Sine x over 2 since it's thing.
What is it?
Sine x over 2, x cubed sine x over 2.
Oh, you mean like some kind of trig identity for cosine? You don't need a trig identity. Yeah. It's not as complicated as that. And plus, a trig identity really helps you with things like cosine of something plus something, cosine of a plus b. Don't have much of a trig identity for division. Yeah. Here, so you're kind of stuck. Like, what is this? Kind of stuck. But here you want to use your intuition because think about it. Okay, so 2 over 0 is like, let's say, really large numbers. Okay. And then cosine of really large numbers, well, they'll be like random numbers. You don't really have a pattern for that. But what's the most cosine could be? 1. What's the least it could be? -1. So you have a bunch of random numbers. Fine, let's just call them random. But they're all between -1 and 1. So I don't know what they are, but they're all between -1 and 1. So whatever those random numbers are, they're getting multiplied by what? 0. So like intuitively, if things make sense, right? The limit should be 0 because even though we don't know what this is, we don't need to. It's something between -1 and 1, and it's getting multiplied by really, really small numbers. So like if we put into our calculator like x equals 0.1, 0.01, yeah, cosine of 2 divided by 0.1 or cosine of 2 divided by 0.01, it'll just spit out random things. But they'll get multiplied by something really tiny. The end result will be really tiny. So how does this work? Okay. So here is the theorem that sort of captures the intuition. Squeeze theorem. Okay. Right. So you should think of this as like in the squeeze theorem, you should think of this like f of x. F of x, really complicated. Okay. But cosine is bounded by 1, which is not so complicated. And it's also bigger than -1, which is not so complicated. So suppose g of x, h of x, you should think of it as nice functions. And f of x is smaller than h of x and bigger than g of x. So you create a little sandwich. So f is smaller than this nice function h, and it's bigger than this nice function g. Suppose this, and suppose we could do the limits of g and h. Suppose g and h are so nice for us that we know their limits. Suppose limit as x goes to a of g of x is equal to L, and it matches the limit as x goes to a of h of x. Okay. So the function on the top of the sandwich and the function below the sandwich, they both have the same limits, right? I'll even put a little remark that it doesn't have to be a. It could even be limit as x goes to a from the right or left. So it doesn't actually matter. You could apply this a goes to right or left. So what does the theorem say? That then limit as x goes to a of f of x is equal to L. Okay. So the function below and above the sandwich, so the two breads of the sandwich, they have the same limit. So that means your complicated thing in the middle of the sandwich has to have the same limit, right? Because this is basically saying that f of x is smaller than h, whose limit is L. So f is smaller than L, but g has a limit L. So f is in between L and L. How could you be in between L and L unless you're also equal to L? Picture, right? What does this mean? The picture here is, maybe I'll use colors. Okay. So your function is crazy complicated, doing weird things. That's your f of x. You have no idea what to do with it. But you realize, you know what? There's a nice function above it. That's h of x. And there's a nice function below it. That's, let's say, g of x. Right? And they have the limit L. Right? These are nice and they have the limit L. Okay. So especially when you're dealing with trig, the way you utilize it is because trig could be very complicated. But what's lying above cosine is the constant function 1. Right? What's lying below cosine? The constant function -1. Right? So you could get rid of things like these trig functions using an inequality. So in our example, so cosine 2 over x, right? Let's forget about the x cubed for a second. But cosine of 2 over x, it's always smaller than what number?
1.
1. Okay. And it's always bigger than what number?
1.
-1. Okay. It's not quite what we need. We need x cubed in front, but that's okay. We can multiply all 3 sides by x cubed. So I'll multiply all 3 sides by x cubed. Multiplication. Okay. So -x cubed is sitting below x cubed cosine of this crazy thing. and x cubed is sitting above x cubed cosine of this crazy thing. Okay, so what the squeeze theorem is saying that rather than doing the crazy thing, you're allowed to just do the limits on the top and bottom of the sandwich. Okay, and if they match up, you'll be done. So what's the limit as x goes to 0 of negative x cubed? Right, here's the limit that we're doing, which is 0. So if I do a 0 limit of negative x cubed, I get 0. All right, x goes to 0 from the right. What about x cubed? What's the limit of x cubed? Yeah, Matt? 0. So this limit also, x goes to 0 from the right, is 0. Right, so what does squeeze theorem say? If they match up top and bottom, then that limit is 0. It didn't have to be 0. The limit might have been like 2 or 1. But this case happens to be 0. Goes to 0 from the right. X cubed cosine 2x equals 0 by squeeze theorem. But you have to be able to do an inequality to use it. You have to, have a little creativity on bounding above and below. Seeing what's lying above F and what's lying below F. Yeah, Matthew?
Is there any other situations for this?
Yeah, in general, like for limits, just anytime you have a limit that you can't do, squeeze theorem is what you usually try to get an inequality. Yeah.
Is it the same for x from the left side?
Yes, it would have been the same thing for x goes to 0 on the left side. Yeah, it would have been the same idea. That's right. Yeah. The only thing it's just a minor technical point. If it was 0 from the left side, just remember from pre-calc, multiplying by x cubed, 0 from the left side means that x cubed is a negative number. Cubing a negative number is negative. So when you multiply with inequalities by negative numbers, you reverse the inequalities. So it won't change the answer. Just if you want to be technically fully right, you'd have to reverse the inequality. Yeah, so that's a good question. Yeah, good.
Yeah, negative.
So that's something you have to know about cosine, is that cosine is always bigger than -1. And then cosine is always smaller than 1. So we need a little background knowledge on what's bounding cosine. Yeah. So that's something we would have to know, that cosine is bounded by 1 and -1. Okay, good. So I think this covers one of your problems on the web assignment. So you can even fill in. Maybe this was 15 or this was 16. So either 15 or 16, you could do something similar. I think it's very similar to this problem. Okay, good. Questions about this problem? I'll do another example of squeeze theorem, but it's a little bit of an art form, right? You have to do an inequality for above and below.
Can you use the squeeze theorem on all limits that has 2 functions?
Well, technically, you can use the squeeze theorem whenever you want, yeah, and any time, but you do need the thing on the bottom and the top for their limits to match up. So if you know how to do the limit of f and it's not so bad by yourself, you might as well do it, right? Squeeze theorem is kind of a last resort where if f is too complicated and you don't know, then you start working with inequalities. Yeah. So a lot of situations in math, in practical situations, yeah, f is too complicated and you need to do a limit, right? So what mathematicians try to do is they try to find g and h where the limit's a lot easier. Right? They try to bound it, try to find a bound for the function. Here, let me do another example. Maybe this one's a little more abstract then. So suppose x squared plus x minus 2. Suppose f of x is some function. And x squared plus x minus 2 over x plus 3. Okay. And they already found the bound for you. So this is the function below. So f of x over, let's say, 2x squared is less than or equal to x squared plus 2x minus 1 over x plus 3. Find limit as x goes to -1 of f of x. So in this case, they didn't tell us what f of x is, but it doesn't matter because the fact that they told us what's above and below it means they want you to do squeeze theorem, right? What they want you to do is instead look at the limit of g of x and look at the limit of h of x instead, right? So squeeze theorem tells you that if the limits of g and h match up, I can get what's in between. Okay, so let's check it. So use squeeze. So I'm going to check left and right. X goes to -1. X squared plus x minus 2 over x plus 3. Okay. What is the function f? It won't matter if the limits top and bottom match up because we have squeeze theorems. We don't even need to know what f of x is. But how do I do a limit like this? Limit as x goes to -1. What should I do first? Plug it in. I hope for the best. This one's continuous, so if I plug in -1, -1 squared is 1. And then what do I write? -1, and then -2 divided by -1 plus 3 is 2. So final answer, I get -1. -1. Okay, so the bottom sandwich, bottom bread, going to -1. All right, just picture the sandwich. Okay, top bread, x squared plus 2x minus 1 over x plus 3. What do I do? Let's see, Lissa? Yeah, just plug it in, and what do I get? Numerator is 1 minus 2, and then -1. And then denominator is -2. Good. -1 plus 3, +2. The final answer, I get 1 minus 1 is 0. -2 divided by 2 is -1. Right. So notice top and bottom of the sandwich, they're both -1. Right. So that squeezes what's in the middle. It has to be -1, so it matches. Matches. Okay, so by squeeze, the limit, oh, question?
Would you have to multiply the initial x squared to each side?
You could multiply it. Yeah, what's Sapphire is saying, I should multiply by 2x squared on each side just to make it easier. Yeah, so that's true. I could either do it first or I could do it now. But I will do that essentially. Yeah. If you multiplied by 2x squared on each side, that's good. You would have gotten a slightly different limit. You'll end up with the same answer. So by squeeze theorem, what's in the middle, notice that this is in the middle. Limit as x goes to -1 of f of x 2x squared. What's in the middle has to be limit equal to -1. So this doesn't quite give me f of x, but I do know that limits can be done in parts. So the limit of a fraction, I could do numerator and denominator separately. So limit as x goes to -1 of f of x in the numerator, divided by the limit of the denominator. What's the limit of the denominator? Limit of 2x squared is just 2. And that's equal to -1. So limit as x goes to -1, f of x is -2. Okay. And I don't need to know what f is, right? If I know the functions above and below it and what they do, it's even better than knowing f. And if we did what Sapphire said, is if we multiplied in the beginning by 2x squared on each side, then that would have worked also. We would have gotten -2 for these limits left and right. So either way, we end up with -2. Okay. Questions?
The very last step.
Oh, this step? Yeah, so I have the limit of a fraction, but one of my limit laws is if I have a limit of a fraction, I could do the limit of the numerator and the denominator separately. So I'm allowed to do that. So I can do the limit of the numerator, which is that. I don't know what f is, so I leave it. And then the limit of 2x squared in the denominator, if I plug in -1, I get 2. Yeah. Does that answer your question a little bit? Yeah. So I'm allowed to do that. Hey, good. Questions on this? Yeah.
So you plugged in -1, right?
Oh, which step? This step?
Yeah.
Oh, you mean in the denominator? Yeah. In the denominator, I plugged in -1 because I'm allowed to do limit of the numerator divided by limit of the denominator.
Okay, so my question is, why did it end up being -2?
Oh, why did it become -2? Yeah, because now I have this fraction is equal to -1, and I care about the numerator. So I multiply 2 on each side to cancel the denominator. Yeah, so I did a little algebra. Right. 1 each side. Okay. Yeah, any questions on this? This is a harder theorem to use, right? You have to have a little creativity making those inequalities, bounding functions like this, so. But at least in terms of the web assigned, so now 15 and 16, you guys should be able to do. Just mimic that. So your web assigned has, I think the problem is a little bit easier on the web assigned. I don't know if it has this 2x squared type of thing in the middle. All you have to do is limit of the top and bottom function. But whatever you have in your web assigned, you have a top and bottom function. Yeah, Rachel.
Multiply like the functions by 2x squared. Can you explain why?
Oh, because this is just algebra, like before we even start doing any limits, right? What Safel is saying is like, why don't I make the algebra a lot easier for myself? And just in terms of algebra, when I have an inequality, I can multiply each part of the inequality by 2x squared to make it easier for myself. I'm allowed to do that. So in the middle, the 2x squareds would cancel. That was his idea. Yeah. And you could have done that. So then your bottom function would be this times 2x squared. And your top function would be this times 2x squared. Yeah, so another way to do it. Okay, good. Other questions on squeeze theorem? Yeah, but best time to use it is when you're dealing with like sine and cosine, infinity, basically. Sine and cosine of infinity. That'll help you. Okay, so that was all part of section 2.3. But can you guys do the WebAssign that's similar to this? Your WebAssign has something slightly different top and bottom, so you just kind of mimic this. Take the Yeah, you guys see how on the WebAssign, that's already top and bottom? So you just have an easier top and bottom than I just did. So you just kind of mimic what I did. But you have a function on the bottom, function on top. So you use squeeze on the bottom and top. Yeah. Okay, so section 2.5. Continuity. Okay. So in this section, we'll delve a little bit deeper, right? We already talked about continuous functions where they help us do limits. We could just plug in the value and then we're done. We're going to go to a little bit deeper on what continuity is. Okay, so C is in domain of f of x. Okay, so we are talking about things that are in the domain. They're not in the domain, right? We don't even talk about continuity. It's just not even defined there. So the definition is f is continuous at C if limit as x goes to C of f of x is equal to f of C, right? Which just means that the limits left and right. Remember, limits are the patterns left and right. So the pattern left and right of the function is matching up with the value of the function, which is f of C. So the picture that you should think about is here's C. And, it could be doing weird things here. It doesn't matter. but it's continuous at C. Okay. And in fact, if this is like A, and this is D, and this is f of x, we would say f of x is continuous on the entire interval from A to D. Right. Basically, it's not jumping anywhere in between A and D. It is jumping at A, that's true. But that's why I put open parentheses. Right, because that's true. It's not continuous at A. That's why I put open parentheses. But everywhere in between, there's no jumping. Right? It's not jumping. It's not jumping. Okay. Who knows why? I also put open parentheses at D. Why is it not continuous at D? Technically, yeah, Lissa?
Because there's no limit on the right side.
Good. Yeah, what Lissa's saying is that, see, part of being continuous is having a limit, which means left and right. It means you have to be able to look to the left and to the right and get a limit. And Lissa's saying, well, D can't be continuous. The function is not even defined on the right. So it doesn't have a limit on the right. There's no limit from the right is D and E. So it's not continuous at D based on that technicality. Okay. Which intervals is F continuous? Okay, so I'm going to draw it for you. It's a little exercise. Here's -1, it does this. One is here. And then 2. And then 3. 4. Okay, so think about it. Stare at the graph. Try to find the intervals where it's continuous. Maybe someone could help us just start us off. Give me one interval where you see it's continuous. You have to pick intervals where it's just not jumping. Where it's not jumping anywhere and it's defined. What's your name? Sean? Let's see, is this Sean Duwadi? Yeah, Sean, what interval would you say?
Negative infinity to -1.
Right, negative infinity to -1. Do I put an open parentheses or a close on -1?
Closed.
Close. So close would be including -1.
Open.
So open, yeah. Okay, so Weber sign, you'd have to put negative infinity to -1. So take a minute, take a look at this, look carefully. Sean's right, that's the first interval. Try to pick out all the intervals where you don't see any weird things happening, it's not jumping anywhere. Okay, so try to write those down. Okay, so let's see, I'll call on somebody else. Let's see. Elaine, what would you say? Can you think of another interval where it's continuous?
Say 2 to 3.
2 to 3? Yeah, 2 to 3, good. 2 to 3. Should I put open parentheses at 2 or close? Open, good. Now it's continuous 2 to 3. Is it continuous at 3?
Yes.
Yes, it's not jumping. Can I go past 3? Is it still continuous past 3? It is. So let's capture that. How far past 3 can I go where it's not jumping?
Right before 4.
Right before 4. So in fact, I could even go 2 to 4. I can even go past 3. And should I put close or open parentheses? Open, good. First of all, it's jumping, but it's also not defined to the right of 4. There's no limit anyways. Okay, good. Okay, someone want to try another interval? We have it's Mia dual.
-1 to 1.
Okay, we have -1 to 1. That's another one, yeah. -1 is not defined, but look, it's not jumping until we get to 1. Let's see, one more. We have Ronaldo
Close 1 to open 2.
from 1 to 2.
Yeah.
Okay, close or open at 1? Closed and close or open at 2? Open. Okay, so we're very close, but notice at 1, being continuous at 1 means there's no jump at 1.
So it'd be open.
Yeah, because we're doing continuous. So maybe you said close just because you saw a closed circle. But continuous means there's no jump. But there is a jump at 1. Yeah, so we'd put open. Okay, so on your web assign, we have any other intervals? No.
It's 4.
X equals 4. So x equals 4, it's actually not continuous at 4. There are a couple reasons why it's not continuous at 4. First of all, to be continuous, the limit has to exist on both sides. So we do need both sides of 4. But even without that, the limit would have to agree with the function, right, to be continuous. But here, there's technically a jump because the limit would be around this y value. But the actual function is at this y value. So either way, there's a jump. Either way, there's a jump. I guess here's another. Suppose I had this. Am I continuous at 4? That's a better question. Are we continuous at 4? So remember, there are a couple of things you have to check. Left and right limits have to match. But not only that, they have to agree with the value of the function. They have to agree. Yeah, so look, the left and right limits, they are matching, right? Over here, but are they agreeing with the function? Right, they're not agreeing. So it's not continuous at 4. At 4. Yeah, it's technically not continuous. Yeah. Yeah, any kind of a jump, you'll put open because it's not continuous there. So at 1, there's a jump, it's not continuous. At 2, it's not even defined, so it's not continuous. At 4, it's technically considered a jump because it's not matching with the limit. Okay. So continuous is basically no weird things. No weird graphs, just, with your pencil, you draw something and you don't lift your pencil off the paper. That's what continuous is. When you draw it without lifting your pencil off. So at 4, in order for me to draw this, I had to lift my pencil and, plot that point. So it's not continuous. Yeah, it would be correct if you did it like this. If you did 2, 3 close 3, 4, that would work. Because you want 3 to be included. Yeah. Elaine?
Could you do open 1, open 4?
Open 1, open 4. Oh, good question. Open 1, open 4. No, because it's technically not continuous at 2. It's not even defined. It's not even defined. In order for me to draw this, oh yeah, you're right. Technically, I could draw this without lifting my pencil like this. So, but it's not defined. It's not defined. It's just not defined. Yeah. So maybe lifting my pencil off the paper is not the best way to tell. Yeah, it's basically, it has to be defined and can't jump anywhere. Okay. So where is function continuous? Okay, so now it's not actually graphing, but for things like this, right, it's not piecewise. It's just, it's undefined somewhere, right? So anywhere that it is defined, it's actually continuous, right? Because we learned this is a rational function. Rational functions, they're continuous wherever they're defined, but what's the domain here? Where is it undefined? Raphael?
Not equal to.
Right, x is not equal to 4, so that's not in the domain. It can't be continuous at 4. It's not even in the domain. So it's continuous on everywhere except continuous on the domain. So negative infinity to 4, 4 to infinity. Another example. G of x is equal to x squared minus 16 over x minus 4. Okay, so where is it continuous? Raphael?
Everywhere.
Everywhere except for it's not defined somewhere.
Same
Be a little bit careful. It's not defined. So domain, it's not really defined somewhere. What's the domain? X is not equal to 4. So it is continuous everywhere except for 4, because it's not even defined. So continuous everywhere except for x equals 4.
And we say that domain and the continuous are same thing.
What's the same thing? Oh, the domain is the same as the intervals of continuity? Yeah, there's not really a terminology for that. It's just they happen to agree. They just happen to agree that it's continuous everywhere on the domain. That's what you would say.
Could you just cancel out x minus 4?
Yeah, so Safael is saying, what can't I cancel out x minus 4? And then this function is really x plus 4, right? So I can't really do that. I can't do that because it's true. I could cancel as long as x minus 4 is not 0. So in algebra, you can cancel two numbers, top and bottom, as long as those numbers are not 0. So I can cancel x minus 4 as long as they're not 0, but I can't cancel 0 divided by 0 because 0 divided by 0 makes no sense. So you're right. I could cancel as long as x is not equal to 4. Okay. But 4 is not in the domain, theoretically. Another way of saying it is just a little note, what Safael is saying, is x squared minus 16 minus x4, question mark, is that the same as x plus 4? If I cancel numerator, top and bottom. So technically, no. Functions are the same if they have the same domain. So, but they have a different domain. Right, so they're technically not the same. No, since different domain. But here, a little bit more in terms of what Safael is saying. Here's really what you want to do. Here's the mathematical way to say like what you're trying to say, that it's the same as x plus 4. So here, I'll show you what this means. So the domain is not equal, x is not equal to 4. But limit as x goes to 4 of x squared minus 16 over x minus 4, it is 0 over 0. So 0 over 0 limit. So limit as x goes to 4, x minus 4 times x plus 4 over x minus 4. Right, since I'm doing a limit here, with a limit, I could cancel. And what's my limit? 8. Okay. Because I have a limit, not continuous at x equals 4, but limit as x goes to 4 of f of x, or this is g of x, is equal to 8. It exists, means that x equals 4 is called a removable discontinuity. I should say it's finite. It's finite. Okay. Right. So if you're discontinuous somewhere, because it's not in the domain, you're discontinuous just because it's not in the domain, but the limit exists, it's called the removable discontinuity. The reason it's called removable is that if we graph g of x, okay, notice that when we cancel x minus 4, it's just a line, x plus 4. So here's 4, and here's 8. So here's the line x plus 4. Here's the graph of g of x. So when that happens, now the limit exists on both sides, but you have a hole. Things like this are called a removable discontinuity. Okay. Removable discontinuity. Why? What does that mean? It just means since we can plug the hole. We can just plug the hole. If all we have is a hole in our graph, that's a removable discontinuity. That's what it is. It's just a hole and there's no point there. So it's removable because we could plug it. You could plug it up, you could put a stopper on the drain. Okay, how do we plug it up? We could define G twiddle right? And what does it equal? G twiddle, well, it's going to be equal to G of X if X is not 4, right? And it's going to be equal to 8 if X equals 4. Okay. This is just all a fancy way of plugging the hole. So our limit was 8. So we'll plug in the hole at 4 with the limit. And what do we get? This is what Safael was trying to get at, is if we plug the hole, we get X plus 4. Right. That's if we plug in that hole with the Y valve. So just the terminology. Yeah, so when you see WebAssign asks you like, is the discontinuity removable? It means you're looking for a hole like this. So the function's undefined, but you do have a limit. You do have a limit that exists, so you could plug it up. Okay, what's not removable? See, notice here it's undefined at 4, right? But if I take the limit as X goes to 4, X cubed minus 9 over X minus 4. Well, if I plug in 4, I get 64 minus 9 over 0. So that's the C over 0 case. Now, the C over 0 case, maybe it'll be infinity, maybe it'll be minus infinity, maybe it'll be DNE, but either way, it's not finite. So not finite. So X equals 4 is not removable. Okay. Removable means I could plug up the hole to make it continuous. It's a nice function. I could plug in that hole, making continuous. If it's something like this, where the limits are infinity, negative infinity, have an asymptote, there's nothing I could plug in to make it continuous, right? It's just always going to remain detached. Right? There's no way I could plug something in so that with an asymptote, I can like connect things together. There's no way. So does that make sense, guys? Removable versus not. So also known as plug the hole versus can't plug the hole. Just made that up, but it's the way to think of it. Yeah, any questions on this? So the difference between these two? So both of these, X equals 4 is not in the domain, but they behave differently. One has asymptotes and one just has a hole we could actually plug up. Plug it up to make it continuous. So we can plug the hole to make it continuous. Okay. Because left and right limits already there. Okay, good. Any questions on this before I remove it? Someone there? No? Okay. Over there. In the back. Okay. We're together so far? Yeah. Yeah. Okay, so here's an exercise that you will, the type of exercise you could have. Find value of A to make f of x continuous. Okay. So what this is going to do is we're going to be dealing with piecewise functions. So they could jump, but they will have this parameter A so that for just the right A, the two pieces will connect together and they won't jump. So that's what they're trying to do. So the example here is f of x is equal to x squared plus a for x less than or equal to 2, and 3x plus 8, f of x continuous everywhere, for x greater than 2. So you guys see how we have two pieces, less than 2 and bigger than 2? Right? They could be far apart from each other, these two pieces, depending on A. But what they're asking is, tell me the A value to bring these two pieces together so it's continuous and there's no jumping around. Okay. Okay, so how do you do this problem? Well, first of all, to the left of 2, if we ignore 2, is x squared plus a continuous? Everywhere to the left? Yeah, it's a polynomial, it's continuous. So we don't have to do anything to the left of 2. And 3x plus 8, is it continuous? To the right of 2? Yeah. So the only thing that matters is at 2. So we need limit as x goes to 2 from the left. We need it to match up with limit as x goes to 2 from the right to make this work, right? To make it continuous, we need left and right to match up. Okay. And you don't need it for this problem, but maybe for other problems, it should equal to f of 2. Okay. Might need this for other problems. Might need for other problems. You don't need it for this problem. Okay. But let's focus here. So limit as x goes to 2 from the left. It needs to match up. Okay. When you do limit of piecewise, you have to figure out which piece we're asking. If we're left of 2, are we using the first or the second function? Left of 2, think about it. Everyone at the same time. 3, 2, 1. First. Is that everyone? It sound like it. Whispers. Okay. Limit x goes to 2 from the left of x squared plus a. X squared plus a is continuous, so what do? I plug in 2. Let's plug in 2, so I get 2 squared plus a. Now you guys try. Now you guys have to do limit as x goes to 2 from the right of f of x. Find out what it is. And then set them equal to each other, because continuous means I don't have a jump. Set them equal to each other, and you could find a. So try to do the limit from the right. Whatever you get, set it equal to each other.
10.
And I'll do this at 4:10. So if you need to take a break, go ahead.
Yeah. Probably right, what? That case you're wrong.
I think no, it's the.
Okay.
Are you using class Monday?
I'll put an announcement. We won't have time.
Okay.
Make an announcement.
Did you say Harry Potter? What about you? You didn't pick me. Fuck. Like, okay, she's really smart. And it's like, okay, she's really smart. And it's like, she's definitely not a Slytherin, so. It's like, wait, shit, she's.
It's like 5 points.
I did it like once, then okay, that's fine.
You see them.
Yeah, like facing the glory. That definitely feels like a me thing. You know, also like a little on the competitors too. So. Like someone kind of competitive. Like I'm in a it's like personal kind of competitive is like a Slytherin, you know? Like yeah, I don't mind why I need to do that. I'm not saying that's you, I'm just saying that's like kind of how it works. They don't really care about glory, they just like knowledge. No, they like they only care about knowledge, they don't care about the like what's their deal? They don't care about shit, they're just loyal. Okay, that's an interesting dynamic. It's a Hufflepuff that die.
Cedric.
Yeah. Yeah. It's shocked when he died. You know, right. Or like it's got so dramatic too. Like, cheer. I never watched like the movie, but I read the book and like that scene just like I was like I saw school that I've been looking for since like literally June. It's like, you know, the beauty of house. all Japanese, Chinese, Chinese, and everything. And it's like, it's mostly so there.
On Monday, like up to 9.
I start at 9 and I have it from 8 on Monday.
I start at 9. I have it up to 9.
I literally had clear skin when I had that stuff. And I was kidding not. I had to water, especially on the rest, nobody makes them. Nobody. Closer, but nobody makes them. Nobody makes them. I don't think we did there.
Day 2. The first.
No.
Really bad.
Oh, yeah.
I have a picture.
How long does it take you to get here?
30 minutes.
Where the hell do you live?
Summers, I don't live that far. No, 30 minutes, 45.
I should go.
I was exhausted.
Okay, guys, let's continue. So what did you pick for 2 from the right? Which function is that? First or second? Second. So the limit as 2 from the right. 3x plus 8. What's that limit? How do I do it? Plug in 2, what do I get? Okay, 3 times 2 plus 8. Right, 14. Right, to be continuous, left and right have to match. So 4 plus a is equal to 14. Right, so what is a? 10. Right. You guys see how to do that? Okay, just make a match. Shortcut, there is a shortcut, but at your own risk. You know, they could vary up the question where the shortcut could confuse you at your own risk. But the shortcut is you just need both of these pieces to match up at 2. So you could just do this in one line if you wanted to. So you need x squared plus a plug in 2 should be equal to 3x plus 8 plug in 2. So they have to match up at 2, right, which is the exact same thing that we did, but kind of the shortcut without writing limits. So if we plug in 2, we get 4 plus a is equal to 14. Okay, so a equals 10. Okay. So yeah, the shortcut works, but it takes limits out of this whole procedure. So you could have more complicated questions where the limits are important. So. Okay, any questions on this? Yeah.
So you get 14 and then you did like 4 plus a equals 10. Like, how did you get that?
Well, I got 14, right? So the limit from the left has to be the limit from the right. So here's the limit from the left that we did. And here's the limit from the right that we did. So to be continuous, they have to match. So 4 plus a has to be 14. So if I subtract 4 from both sides, a gives me, a is 10.
Just figuring out what a is.
Exactly, yeah, yeah. So here's what the problem will be worded. Find the value of a.
Intersecting.
Yeah, so the problem will even tell you, you have to figure out what a is. If a was not 10, if a was 9, it would jump. So a is exactly what you need, so it's not jumping. The pieces are connected. Yeah, good question. This makes sense, guys?
At your own risk.
Which part?
At your own risk.
Oh, at your own risk, the shortcut, yeah. So there could be problems where this doesn't work. There could be problems where this shortcut doesn't work. See, with limits, you won't mess up because you're doing a limit. So that's really what it is. But what would be a place where it doesn't work? Well, what if you had something like, instead of x squared plus a, you might have like x squared minus 4 divided by x minus 2. something like that. So then you're gonna, I'll just use the shortcut because I hate limits. I want to avoid limits at all costs, so I'll use the shortcut. So I'll just plug in 2. And what students write on their exams or whatever, I'll just plug in 2. It's 0 over 0. That sounds good. 0 over 0. Nothing wrong with that. And then they set it equal to something and say a bunch of other things that don't make sense and just propagates. Okay, so at your own risk. So you could do this as long as you understand what you're doing. Okay, just understand that it's a shortcut to actually doing limits. But yeah, so at your own risk, but up to you. With limits, you won't have this problem. So, because we know how to do 0 over 0 limits. Okay, let's try another example. Find A and B to make f of x continuous. A and B. Okay. So f of x is equal to 2x minus 1 for x less than -1, ax plus b for -1 less than or equal to x less than or equal to 1, and then 7 for x greater than 1. Okay. Right, so because you have pieces, things could jump. So the first thing you have to figure out is which x value is a possible jump. Which x value? You should be able to just look at it and say, which x value I might have a jump. It's problematic. You guys see? It's where you transition from one piece to the other. Sandra, you were saying? Yeah, -1 is a piece. Yeah, why is -1 bad? Yeah, because we're transitioning from the first to the second. What other x value is bad? Yeah, Cameron? 1, why?
Because you're jumping from values from a of x plus b to 7.
7, yeah, good. Like Cameron's saying, we're jumping from the second to the third at 1. So the x values that you jump, you have to realize those are your problem areas. So what we need is limit as x goes to -1 from the right to match up with the limit as x goes to -1 from the left, right? So we make sure it doesn't jump. The limits have to match so it doesn't jump, and we need limit as x goes to 1 from the right to match up with limit as x goes to 1 from the left of f of x. And if you want to use the shortcut to do that, that's fine. But just realize that that's what we're doing. So -1 is a transition. 1 is a transition. So left and right have to match. So I'll give you guys a couple minutes to try it. So try it. Do the -1 limit from the right, do the -1 limit from the left, set them equal. Yeah, Jackie?
So is it always gonna be the numbers transitioning between the pieces?
Yeah, you could always look on this right side and look at these numbers. Those are going to be the transition points. Yeah, so this number is where the first function ends and the second one begins. That's the -1. And 1 is where the second function ends and then you start the third function. Yes. So these numbers will tell you the transitions. They won't tell you what to do in the problem, so you have to figure out that it's -1 and 1. Okay, but just try it. Try it and set it equal to each other.
Equals 5 and b equals 2.
Careful, you're trying to give an answer? Okay, yeah, we'll work through it. We'll work through it, yeah. And if anyone wants me to check, I'll go around and check. I can check it.
답은 보여서 막
That's the first one.
Okay, plug them in, send me. Yeah, so try the last problem. So you have to do this limit. Negative one. The right of negative. First one, yeah. Here you want to use the second function and plug in -1. And to the left of -1.
That's how I stopped this, but how do you know this? Like, how do you, is there like, do I just have to go through every combination of 7 that could possibly be added?
Good.
Like, it's 6 and 1, 5 and 2, right? These are the options. Like, you have to look at the other one to figure out what A and B is. Because there has to be some sort of output. You know, this machine is.
Leave it there. You can't really do much else. Now you want to here. Try to do something simple. You'll get 2 equations.
No, that's wrong. That would mean that would be negative. I don't know.
Okay, guys, so the idea is we do have to do these 4 limits. So -1 to the right, which function is that? First, second, or third? Remember, it's just a little bit to the right of -1. So is that first, second, or third? Second. So that's ax plus b. So that's ax plus b, and we're going to plug in -1. And that should be equal to -1 to the left is which function? First, second, or third? First. So 2x minus 1 with x equals -1. I should write x equals -1. So I get minus a plus b is equal to -3. Okay. So if you're wondering like, oh, I'm stuck, what's a and b? Don't worry, you're not stuck. What you need is you need to get another equation with a and b. So now do these limits, do something similar with one from the right and left and get another equation with a and b. So you'll have 2 equations with a and b. Then you solve for a and b. Really? Do you have a question?
I'm gonna add a.
I don't know how good. If 7. No, wait. I'm supposed to add. Oops. That's one there. And then you should have 5 here. And 7 is. Oops. I think.
Okay.
We didn't do it.
Yeah, so one from the right is which function, first, second, or third? Third, so it's which, so just 7, and that should be equal to one from the left is which function? Second, right? So that should be ax plus b, where we're gonna plug in 1. So 7 is equal to a plus b. Okay. Now you just do however you're taught in algebra, where you have 2 equations, 2 unknowns. Elimination method is 1, or substitution, so you have a plus b equals 7. I could add these together, and I get 2b is equal to 4. Okay, it's one way to do it, or substitution, so b is equal to 2. Then I could plug it back in, so a plus 2 equals 7, so a equals 5. Yeah, so don't get stressed out if you get an equation with a and b and you're like, what do I do next? That's fine. So just get another equation with a and b. So you have 2 unknowns, you'll have 2 equations. It'll work out. Okay, any questions on this, guys? Does it make sense what to do? Okay, remember, this part is not given in the problem. You have to figure this out yourself, that you have to use -1 and 1. Okay, you guys will have to figure that out for yourself. You look at these transition points, which are -1 and 1. Okay, see other questions? Okay, thumbs up if this made sense. Thumbs down, this is bad. Yeah, Matthew,
The same problems again.
like a similar one like this? Yeah, here you could try this one. Yeah, let's right. This one's similar. F of x is equal to 3x squared plus a for x less than 1. 10 for x equals 1. 20x over b for x greater than 1. Okay. Okay. Notice that 1 is the only transition value, but you're still going to get 2 equations because not only do the limits at 1 have to match, but it also has to match with f of 1, right? Because if the definition of continuity, let me put it up again. Remember the definition of continuity? Not just the left and right, it also has to match with the function value. So you guys could still get 2 equations by using the x equals 1 as well. So try that. Okay, try to get 2 equations. Or, yeah. So find a and b. If you weren't sure, I wrote down what equations you'll have. You'll have left limit should be equal to f of one. Right limit should be equal to f of one. They're all equal to each other. Okay, limit one from the left. Which function do we use? First, second, or third? First one. We plug in one, what do we get?
3 plus.
3 plus a. What's f of one? And one from the right, first, second, or third? Third. Right of one. We plug in one, what do we get?
20 over b.
20 over b. Okay, so this should be all we need. Actually, we could just solve for a here. So a is 7, subtract 3. And for b, well, what would b have to be? 2. It would have to be 2. Okay, so very similar flavor, little variation. So yeah, in this case, we had to use that the not only left and right limits match up, they also match up with the function. So you see the difference. Okay. Then there won't be any hole. It'll just, these three pieces will all match up at x equals 1. Y value will be 10. Okay. An easier problem than they could ask you, slightly easier, but it's the same idea, less work. Is f of x continuous at x equals 2? E to the x plus 3, x squared plus 100. This is x less than 2. And this is x greater than or equal to 2. So is it continuous? That is the question. No, the answer is yes or no. Not I don't know, but either yes or no.
No.
Okay, what do we have to do to check for continuous? What should we do?
2,
Right, plug in 2 to where?
both of them,
To both and see
they match.
they match. Right, continuous means that at 2 is the transition zone where we go from the first to the second function. They need a match. So try, guys, plug in 2, see if it matches. So e squared plus 3. Does it match? Question mark with 2 squared plus 100. Those equal? No, right? So left and right limits are different. They're jumping. Pieces are jumping. So the answer will be no. That kind of thing. To be more explicit, limit as x goes to 2 from the left is not the same as limit as x goes to 2 from the right. Okay. Any questions on this? Yeah, you guys see the types of questions they're asking here? Okay, so it's all the definition of continuity. And it's all this idea of not jumping. So. Okay, so if you guys look at your WebAssign for. This is 2.5. 2.5, not so many questions, but let's see, what's a similar one? Yeah, so try to do like number 4 and 5. You know, if you have your WebAssigns, I'll take a look, and then I could take a look at what you guys do. Okay, so see if you can get number 4 and 5 done.
Well, WebAssign doesn't load when I'm in this room.
It doesn't load when you're in this room? Not even on your phone or anything?
Or I can try and help you.
Yeah, you just want to get like the numbers. And then I'll go around and check. Yeah, so if it's not loading, you just try these, I guess.
Yeah, I'll just try them. The numbers will be different, though, right?
Yeah, they'll be slightly different, so you might have to adjust. Is anyone else having problem loading? Okay. Yeah, so Matthew, I'll just put yours up, and then you'll see the numbers of yours.
It's like it's on the infinite span.
Yeah, so here are your numbers that you could write down.
Thank you.
Yes, just write it down for yourself. 3 and 4. Okay, and then for number 5, here are your numbers for number 5. You could write that down. Yeah, do you have them down? You have them down. Okay, so if anyone needs me to check their work, let me know. Let's see, Jackie,
Mean again in this situation,
what is it?
what does finite mean in this situation? Finite.
Finite.
So this one.
That's fine.
You actually get a number that if you take the limit as x goes to three, that means you do left and right, you get a number out of it. That's what it is. It's not infinity, it's not negative. And it's not DNE, you actually get a limit, finite.
Okay,
Probably like a 0 over 0 limit, so just take left and right and see if you get infinity. And if you don't, and you actually get a number that matches left and right, that's what it means to be finite.
okay.
So the graph would be x equals 3 and then it's 1.
Oh, yours is this one. Should have balanced. You have 16C on the left, and you have 4C on the right. So yeah, you should combine those. Bring the 4C to combine the C's. Yeah, good. Thank you. Thank you.
Do it or something. That was the one last year. They probably changed this.
Not infinity.
So yeah, these are. We finished it.
Yeah. She find out records. But another thing you put to one should be left right. So that'll narrow it down. It's also one to find the negative. Then it should be left. You start getting what's in there. That'll also happen. Yeah, that's right. Right, there will be a But it must be either this one or that one. The way you decide is you'll be left, right? See if you're getting positive or negative.
Yeah, but you're supposed to plug in the same thing for everything. So am I supposed to plug in like three?
No, it's.
So one half, the first half, I guess the before is two. But then how are you married? Because I guess
It
there's
was
no issue.
-1 and then
There's
one.
no issue.
Yeah,
with
it's
two numbers. You can
yeah.
Okay, thank you.
Divide by 42.
Thank
So
you.
we had.
You're welcome.
Okay, don't
Okay,
put an
so-
adjustment. I when I need.
Let's see. Python. C plus plus.
Yeah, I remember in freshman year, I ran Java. I was not good at.
If it's here, it's gonna. Right? It's. Is this? I don't know which graph it is. This is right? This is a 2.5.
Yeah.
I know it's not.
It's
You know what I remember, Richard?
That's it.
Yeah, so remember, guys, questions like number 5, if you just try to plug in 2 for this first function, you'll get 0 over 0. Right, so that's why you have to remember, we're actually doing limits. We're not just plugging in, we're doing limit of 2. So it's a 0 over 0 limit. You have to do algebra to cancel things.
the correct way. Yeah, she's the year younger. She lived in New Jersey.
Okay, we'll pause here, guys, and if you have any questions, let me know. Let me know. Have a good weekend. I'll put out an announcement that